Picture this. 2.5 million light-years away, a massive galaxy containing 1 trillion stars is racing toward us at 250,000 miles per hour. The Andromeda Galaxy and our Milky Way are locked in a gravitational embrace that will culminate in the most spectacular cosmic event our local universe will ever witness. In 4 billion years, these two galactic titans will collide, merge, and create something entirely new. And here's the incredible part. We already know how this cosmic dance will unfold thanks to cutting-edge telescopes and supercomputer simulations that let us peer billions of years into our own future. If you find yourself fascinated by the mysteries of our universe, hit that subscribe button and leave a thumbs up. Now let's begin. Right now, as you're watching this video, the Andromeda Galaxy is hurtling toward us at about 250,000 miles per hour. That sounds terrifyingly fast, doesn't it? But here's the thing, space is so incredibly vast that even at this breakneck speed, the collision won't happen for another 4 billion years. To put that in perspective, that's almost as long as Earth has existed. Let me paint you a picture of what we're dealing with here. The Milky Way, our home galaxy, contains somewhere between 200 and 400 billion stars. Andromeda? It's even bigger, with about 1 trillion stars. When these two cosmic giants meet, it will be the most spectacular light show the universe has ever produced in our cosmic neighborhood. But how do we even know this collision is going to happen? This is where the story gets really interesting. Back in 1912, an astronomer named Vesto Slipher was studying Andromeda at the Lowell Observatory in Arizona. He discovered something that shocked the scientific community. Unlike almost every other galaxy we can see, Andromeda is moving toward us, not away from us. You see, the universe is expanding. Edwin Hubble proved this in the 1920s when he showed that most galaxies are moving away from each other, like raisins in a rising loaf of bread. But Andromeda is different. It's close enough that gravity overcomes the expansion of space, pulling our two galaxies together in a cosmic dance that started billions of years ago. Modern telescopes have given us an even clearer picture. The Hubble Space Telescope, launched in 1990, has captured stunning images of other galaxy collisions happening right now across the universe. These collisions show us exactly what's in store for our own galaxy. The Gaia Space Telescope, launched by the European Space Agency in 2013, has been mapping the positions and movements of billions of stars with unprecedented precision. This data has helped astronomers create incredibly detailed simulations of what will happen when Milky Way meets Andromeda. Now you might be wondering, what exactly happens when two galaxies collide? Will stars crash into each other in massive explosions? Will planets be flung out into the cold darkness of intergalactic space? The answer might surprise you. Despite containing hundreds of billions of stars each, galaxy collisions are actually remarkably peaceful events, at least for the stars themselves. Why? Because space is mind-bogglingly empty. To understand just how empty, imagine this. If our sun were the size of a ping-pong ball in New York City, the nearest star, Proxima Centauri, would be another ping-pong ball in Los Angeles. That's how much space there is between stars. When Andromeda and the Milky Way collide, the chances of any two stars actually hitting each other are virtually zero. It would be like two swarms of gnats passing through each other. They might look like they're colliding from a distance, but up close, each gnat has plenty of room to fly past the others. But that doesn't mean nothing happens. Oh no, the effects will be spectacular. The gravitational forces at play will completely reshape both galaxies. Stars will be pulled in new directions, creating beautiful tidal streams that stretch across space like cosmic ribbons. Some stars will be flung out into intergalactic space, destined to wander alone in the darkness. Others will be pulled into new orbits, finding themselves in completely different neighborhoods of the newly formed galaxy. The real action happens in the gas clouds. Unlike stars, which are relatively small points in space, gas clouds are enormous and diffuse. When the gas clouds from both galaxies collide, they'll compress and heat up, triggering the birth of millions of new stars. Astronomers call this a starburst, a period of intense star formation that lights up the galaxy like a cosmic fireworks display. We can see this happening right now in other colliding galaxies. The Antennae galaxies, located about 45 million light-years away, are in the middle of their collision. Hubble's Space Telescope images show brilliant blue star clusters where new stars are being born by the millions. The Cartwheel galaxy shows us what happens a few hundred million years after the initial impact, a beautiful ring structure created by the shock wave of the collision. But what about Earth? What about us? This is where the story becomes deeply personal, because we're not just observers of this cosmic event, we're participants. Our sun, our planet, and yes, even you and I are made of atoms that will be part of this galactic merger. The good news is that our solar system will almost certainly survive intact. The sun and its planets are gravitationally bound together much more strongly than the galaxy as a whole. We might find ourselves in a different part of the new galaxy, perhaps further from the center, or maybe even in what astronomers call the halo, the sparse outer regions. But Earth, if it still exists in 4 billion years, will continue orbiting the Sun, just as it does today. Of course, I should mention that in 4 billion years, Earth will face challenges that have nothing to do with the galactic collision. Our Sun is slowly getting hotter as it ages, and in about 1 billion years, it will be hot enough to boil away Earth's oceans. By the time Andromeda arrives, the Sun will be nearing the end of its life, preparing to expand into a red giant star. But that's a story for another day. What's truly fascinating is that we can actually see what our night sky will look like as Andromeda approaches. Right now, Andromeda appears as a faint, fuzzy patch in the constellation of Andromeda. Surprise, surprise. Under dark skies, you can see it with the naked eye. It's the most distant object visible without a telescope at 2.5 million light-years away. But as the eons pass, Andromeda will grow larger and larger in our sky. In about 2 billion years, it will appear as large as the full moon. Can you imagine looking up and seeing an entire galaxy stretching across the sky? By 3.75 billion years from now, Andromeda will dominate the night sky, its spiral arms clearly visible, its trillion stars creating a second Milky Way across the heavens. NASA scientists have created stunning visualizations of this approach using supercomputers. They've simulated the gravitational interactions of billions of stars, tracking how each galaxy will distort and reshape the other. These simulations show that the collision won't be a single event, but a long, drawn-out dance lasting hundreds of millions of years. First, the galaxies will make a close pass, their spiral arms reaching out toward each other like cosmic tentacles. The gravitational tides will pull streams of stars from each galaxy, creating long, graceful arcs in space. Then they'll swing apart, only to fall back together again. This cosmic dance might repeat several times before the galaxies finally merge into one. The final result? A giant elliptical galaxy that astronomers have already nicknamed Milkomeda, or Milkdromeda. This new galaxy will be roughly spherical, having lost the beautiful spiral structure that both the Milky Way and Andromeda currently possess. It will contain about 1.5 trillion stars, the combined stellar population of both galaxies, plus new stars born during the collision. Speaking of the Milky Way's incredible structure, if you want to truly understand the scale and complexity of our galactic home, before it merges with Andromeda, check out my video, How Big is the Milky Way? In that video, I dive deep into how missions like Gaia, Hubble, and Spitzer have revolutionized our understanding of our galaxy's size, its beautiful spiral arms, star-forming regions, and those ancient globular clusters that orbit around it. The link is in the description and on the card above. Now let's continue this journey. Here's something that might surprise you. We're not just waiting for this collision. It's already affecting us. The Milky Way and Andromeda aren't alone in space. They're part of what astronomers call the local group, a collection of more than 80 galaxies bound together by gravity. The two giants have been influencing each other's evolution for billions of years. In fact, there's evidence that our galaxies have interacted before. Streams of stars between the galaxies suggest previous close encounters. The Magellanic Clouds, two small galaxies that orbit the Milky Way, show signs of being disturbed by Andromeda's gravity even at this distance. We're all part of a cosmic web of gravitational interactions that has been shaping our corner of the universe since these galaxies first formed. Recent discoveries have made this picture even more complex. The Triangulum Galaxy, the third largest galaxy in our local group, might also be involved in the collision. Some simulations suggest it could merge with Milkomeda later, or it might be flung out into intergalactic space. Dozens of smaller dwarf galaxies will be swept up in the merger, their stars added to the growing galactic giant. This brings us to one of the most profound realizations in astronomy. Galaxy collisions are not destructive events, but creative ones. They're how galaxies grow and evolve. They're how new stars are born and how the universe builds its largest structures. Every large galaxy we see, including our own Milky Way, is the product of countless mergers over cosmic time. The Milky Way itself is a cannibal. Right now, it's in the process of absorbing several smaller galaxies. The Sagittarius dwarf galaxy is being torn apart by our galaxy's gravity, its stars streaming across our sky in a path that astronomers can trace. The Canis Major dwarf galaxy is meeting a similar fate. These smaller mergers are like appetizers before the main course of the Andromeda collision. We can see this process happening throughout the universe. The James Webb Space Telescope, launched in 2021, has shown us galaxies colliding in the early universe just a few 100 million years after the Big Bang. These ancient collisions built the first large galaxies, setting the stage for everything that came after, including us. Think about that for a moment. The atoms in your body, the carbon in your DNA, the iron in your blood, the calcium in your bones, were forged in the hearts of dying stars. Those stars were part of galaxies that merged and collided over billions of years. You are literally made of cosmic collisions. You are stardust, yes, but more than that, you are the product of a universe that builds complexity through cosmic catastrophes that are actually acts of creation. This perspective changes everything about how we see the coming collision. It's not a disaster to be feared, but a transformation to be celebrated. It's the universe doing what it does best, creating new things from the merger of old ones. It's evolution on the grandest possible scale. But what will this mean for life in the universe? If Earth is long gone by the time the collision happens, where might life exist? And this is where things get really interesting. The merger will create new opportunities for life throughout the galaxy. As gas clouds collide and new stars form, they'll create new planetary systems. Some of these planets will be in the habitable zones of their stars, where liquid water can exist. The starburst triggered by the collision will create millions of new stellar nurseries. Each of these nurseries could birth hundreds or thousands of new stars, and many of those stars could have planets. We're talking about a galaxy-wide baby boom that could create billions of new worlds. Some of these worlds might develop life, and some of that life might evolve intelligence, looking up at their night sky and wondering about their place in the universe, just as we do now. There's something deeply poetic about this. As our own world faces the natural end of its habitability, the collision that might seem like an ending is actually creating new beginnings elsewhere. The universe doesn't mourn the loss of individual worlds, it simply creates new ones. Life, in whatever form it takes, could continue in Milkomeda for trillions of years to come. Recent research has given us even more insight into what these new worlds might be like. Studies of other galaxy mergers show that the intense star formation creates a wide variety of stellar environments. Some regions will be packed with hot, young blue stars that burn bright and die young. Others will have more stable, sun-like stars that could nurture life for billions of years. The diversity of environments in Milkomeda will be staggering, but here's where modern astronomy gets really wild. We're not just studying this collision to satisfy our curiosity. We're studying it to understand our own origins. You see, the Milky Way has been through this before. By studying the positions and movements of stars in our galaxy, astronomers have discovered the ghosts of ancient galaxies that merged with ours billions of years ago. The Gaia Space Telescope has been revolutionary in this detective work. By measuring the precise positions and velocities of over 1 billion stars, Gaia has revealed streams and clusters of stars that move together, the remnants of smaller galaxies that the Milky Way consumed in its youth. We've identified at least 20 of these galactic fossils, each one telling a story of a cosmic collision that helped build our galaxy. One of the most significant was a galaxy astronomers call Gaia Enceladus. About 10 billion years ago, this galaxy, roughly 1/4 the size of the Milky Way at the time, collided with our galaxy. The merger was violent, heating up the Milky Way's disk and scattering stars into a puffy halo around our galaxy. Many of the stars you see in the night sky are actually immigrants from this ancient galaxy. This discovery has profound implications. It means that our Sun, our Earth, and we ourselves might not have existed without these ancient collisions. The merger with Gaia Enceladus likely triggered a burst of star formation that included the gas cloud that would eventually become our solar system. We are children of cosmic collisions, and this brings us to one of the most beautiful aspects of the Andromeda collision. It connects us to the grand story of the universe. We're not separate from the cosmos, watching it from the outside. We're part of it, made from it, and participating in its ongoing evolution. The collision with Andromeda is just the next chapter in a story that began with the Big Bang and will continue long after our Sun has died. Modern telescopes have shown us that galaxy collisions are happening everywhere, all the time. The Hubble Ultra-Deep Field, one of the most famous astronomical images ever taken, shows thousands of galaxies in a patch of sky no bigger than a grain of sand held at arm's length. Many of these galaxies are in various stages of collision and merger. It's a cosmic dance floor where galaxies pair up, merge, and create new cosmic entities. The Spitzer Space Telescope, which observed in infrared light, revealed even more collisions hidden by dust. The Chandra X-ray Observatory showed us the hot gas between colliding galaxies, heated to millions of degrees by the shock of impact. Every wavelength of light tells us something new about these cosmic crashes. But perhaps the most exciting discoveries have come from gravitational wave detectors like LIGO and Virgo. While these instruments are designed to detect the ripples in space-time from merging black holes and neutron stars, they've also given us new insights into galaxy collisions. You see, when galaxies merge, their central supermassive black holes eventually merge too, creating gravitational waves that we might one day detect with space-based observatories. The Milky Way's central black hole, called Sagittarius A star, has a mass of about 4 million suns. Andromeda's central black hole is even more massive, weighing in at about 100 million suns. When these two monsters eventually merge, they'll create gravitational waves that will ripple across the universe. It will be one of the most energetic events in the cosmos, converting more energy into gravitational waves in a few minutes than our sun will produce in its entire lifetime. But don't worry, we'll be nowhere near this cosmic cataclysm. The black holes are in the centers of their galaxies, thousands of light years from any habitable planets. The merger will be spectacular but distant, like watching fireworks from a safe distance. This raises an interesting question that astronomers are still debating. What will happen to all the stars near the galactic centers? Some will be flung out by the gravitational slingshot effect as the black holes spiral toward each other. These stars will become hypervelocity stars, racing through space at speeds of millions of miles per hour. We've actually discovered several of these speed demons in our own galaxy, likely ejected by past interactions with our central black hole. Other stars might find themselves in stable orbits around the merged black hole, creating a dense stellar cluster at the heart of Milkomeda. These stars will have front-row seats to one of the most extreme environments in the universe, orbiting just light years from a black hole with the mass of 100 million suns. The European Space Agency's future LISA mission, planned for launch in the 2030s, will be able to detect gravitational waves from merging supermassive black holes across the universe. When it does, it will give us a preview of what will happen when our galaxy's black hole meets Andromeda's. We'll be able to study these cosmic mergers in real time, watching as space itself ripples and distorts from the violence of the collision. But let's zoom out even further and consider what this collision means for the universe as a whole. The merger of the Milky Way and Andromeda is just one small event in a universe containing 2 trillion galaxies. Right now, similar collisions are happening everywhere. In the constellation Corvus, the Antennae galaxies are showing us what the early stages look like. In the constellation Serpens, the ARP 220 group shows us a more advanced merger. Every stage of galactic collision is playing out somewhere in the observable universe. This cosmic recycling process has been going on since the first galaxies formed, just a few 100 million years after the Big Bang. The James Webb Space Telescope has shown us these ancient galaxies, small and irregular, nothing like the grand spirals we see today. Through billions of years of mergers and collisions, these galactic building blocks assembled into the large, beautiful galaxies we see today. And here's something that might blow your mind. The process is accelerating in some parts of the universe. In galaxy clusters, where hundreds or thousands of galaxies are packed into a relatively small space, collisions are common. The Coma cluster, about 300 million light-years away, is a cosmic demolition derby where galaxies are constantly interacting, merging and reshaping each other. But our local group is relatively quiet. After the Milky Way and Andromeda merge, there won't be another major galaxy to collide with. Milkomeda will be the dominant galaxy in our corner of the universe, a cosmic island containing over 1 trillion stars. The smaller galaxies in the local group will eventually be absorbed, but these will be minor events compared to the main merger. This isolation has profound implications for the far future. As the universe continues to expand, other galaxy groups will move away from us, eventually disappearing beyond the cosmic horizon. In about 100 billion years, Milkomeda will be alone, surrounded by darkness, unable to see any other galaxies in the universe. Future astronomers in Milkomeda might never know that the universe contains trillions of other galaxies. They'll all be too far away to see. But that's a problem for civilizations trillions of years in the future. For now, let's focus on the immediate effects of the collision. And by immediate, I mean the next few billion years. One of the most fascinating aspects is how the collision will affect star formation in both galaxies. Right now, the Milky Way forms about 1 to 2 new stars per year. It's a modest rate, suitable for a mature galaxy that has already converted most of its gas into stars. Andromeda is similar, perhaps forming stars slightly faster. But when the galaxies collide and their gas clouds smash together, the star formation rate could increase by a factor of 10 or even 100. This starburst phase will be spectacular. The merged galaxy will glow with the light of millions of young, hot stars. Many of these stars will be massive blue giants, burning through their fuel in just a few million years before exploding as supernovae. The galaxy will be like a cosmic fireworks show, with supernovae popping off every few years instead of every few centuries. These supernovae will enrich the galaxy with heavy elements, what astronomers call metals. Every explosion will scatter elements like carbon, oxygen, iron, and gold into space, where they can be incorporated into new generations of stars and planets. This is how the universe builds complexity, turning simple hydrogen and helium into the rich periodic table of elements we see today. NASA's Roman Space Telescope, scheduled for launch in the mid-2020s, will study thousands of supernovae across the universe. By understanding how these stellar explosions work, we'll better predict what will happen during Milkomeda's starburst phase. We'll know how many heavy elements will be created and how they'll be distributed throughout the new galaxy. But here's where things get really interesting from a philosophical perspective. All this talk of collisions and explosions might sound violent and chaotic, but there's a deeper order at work. The laws of physics that govern these cosmic events are the same laws that govern the atoms in your body. Gravity, electromagnetism, the strong and weak nuclear forces. These fundamental forces shape everything from subatomic particles to galaxy clusters. When we study the collision of the Milky Way and Andromeda, we're really studying ourselves. We're understanding how the universe builds complexity from simplicity, how it creates islands of order in a sea of entropy. We're seeing how the cosmos writes its own story, with galaxies as the main characters and collisions as the plot twists. And what a story it is. Consider this. Every atom heavier than hydrogen in your body was forged in a star. That star was part of a galaxy. That galaxy underwent collisions and mergers that triggered the star's formation. Without those ancient collisions, the atoms that make up your brain, the very atoms that are contemplating this cosmic collision right now, would not exist. You are thinking about galaxy collisions with a brain made by galaxy collisions. How's that for cosmic connection? This deep connection between the cosmic and the personal is what makes astronomy so profound. When we look at Andromeda through a telescope, we're not looking at something separate from us. We're looking at our future dance partner, the galaxy that will help reshape our cosmic home. We're looking at the next chapter in our own story. Recent observations have made this connection even clearer. The ALMA telescope array in Chile has shown us star-forming regions in incredible detail, revealing how gas clouds collapse to form new stars and planets. The Very Large Telescope in Chile has detected planets around other stars, showing us that planet formation is common throughout the galaxy. Every new discovery reinforces the idea that we're part of a living, evolving universe. But what about dark matter? Now we're getting to one of the biggest mysteries in the collision story. Both the Milky Way and Andromeda are surrounded by massive halos of dark matter, invisible material that we can only detect through its gravitational effects. In fact, dark matter outweighs normal matter by about 5 to 1 in both galaxies. When the galaxies collide, their dark matter halos will merge too. But unlike normal matter, which can collide and heat up, dark matter particles pass right through each other. the dark matter halos will simply combine, creating an even more massive halo around Milkomeda. This invisible collision will be just as important as the visible one, shaping how the merged galaxy evolves. We've learned about dark matter's role in galaxy collisions by studying events like the Bullet Cluster, where two galaxy clusters collided about 3.7 billion years ago. X-ray observations show the hot gas from the collision, while gravitational lensing reveals where the dark matter ended up. Surprisingly, the dark matter sailed through the collision while the normal matter got stuck in the middle, proving that dark matter really doesn't interact with anything except through gravity. The Euclid Space Telescope, launched by the European Space Agency in 2023, is mapping dark matter across the universe. By the time Andromeda gets close, we'll have a much better understanding of how dark matter behaves in galaxy collisions. We might even know what dark matter actually is, one of the holy grails of modern physics. Speaking of mysteries, here's another one. What role do magnetic fields play in galaxy collisions? Both the Milky Way and Andromeda have galactic magnetic fields, invisible force fields that shape how gas moves and how cosmic rays travel. When the galaxies collide, these magnetic fields will tangle and reconnect, potentially creating spectacular auroras on planets throughout both galaxies. The SOFIA Airborne Telescope, before its retirement in 2022, mapped magnetic fields in nearby galaxies. The data showed that magnetic fields can channel gas flows during collisions, affecting where new stars form. In some cases, magnetic fields can even prevent gas from cooling and forming stars, creating dead zones in the merged galaxy. But let's bring this back to Earth, or rather, to whatever intelligent life might exist when the collision happens. Imagine being an astronomer 4 billion years from now, and let's be optimistic and assume intelligent life has survived and thrived. The approaching Andromeda galaxy would dominate not just astronomical research, but culture, religion, and philosophy. Think about how different cultures on Earth have interpreted the Milky Way. As a river of souls, a bridge to the afterlife, spilled milk from the goddess Hera. Now imagine having two such rivers in the sky, slowly approaching each other. What myths would arise? What philosophies would develop? The collision would be more than a scientific event. It would be a cultural and spiritual milestone for any civilization witnessing it. And the view would be absolutely breathtaking. As Andromeda grows larger in the sky, its spiral arms would become visible to the naked eye. Individual star clusters would sparkle like diamonds. Nebulae, the stellar nurseries where new stars are born, would glow pink and green with the light of ionized hydrogen and oxygen. The night sky would be a constantly changing canvas of cosmic art. Professional astronomers of that era would have the show of a lifetime. They could study star formation up close as gas clouds collide. They could watch stellar streams develop in real time. They could observe the supermassive black holes approaching each other, testing theories of gravity in the most extreme conditions imaginable. It would be a golden age of astronomy. But here's a sobering thought: will there be anyone around to see it? 4 billion years is an almost incomprehensible amount of time. For perspective, complex life has only existed on Earth for about 600 million years. Humans have only been around for about 300,000 years. Civilization is only about 10,000 years old. Projecting 4 billion years into the future is like asking an amoeba to predict the internet. Yet this uncertainty is part of what makes the story so fascinating. We're talking about the deep future, a time so distant that anything could happen. Maybe humanity will have spread throughout the galaxy. Maybe we'll have evolved into something unrecognizable. Maybe we'll have given way to other forms of intelligence, artificial, alien, or something we can't even imagine. Or maybe Earth's story will have ended and the collision will play out unseen and unrecorded. But here's what we do know: the universe will continue its grand experiment whether we're here to watch or not. Stars will be born, live out their lives, and die. Planets will form and evolve. And somewhere in Milkomeda, on some world we can't even imagine, life might emerge and look up at the sky in wonder, just as we do now. This brings us to an important point about the collision timeline. When astronomers say the collision will happen in 4 billion years, that's actually just the beginning. The first close pass will be dramatic, but the galaxies won't immediately merge. They'll swing past each other, loop around, and come back for another pass. This cosmic dance could last for hundreds of millions of years. Computer simulations show fascinating details about these multiple passes. During the first encounter, the galaxies might pass within 100,000 light-years of each other. That's close enough for their spiral arms to overlap, creating bridges of stars and gas between them. Some stars will be exchanged, Milky Way stars ending up in Andromeda and vice versa. It's like a cosmic hostage exchange, but with stars instead of people. The second pass will be closer and more violent. By this time, both galaxies will have lost their clean spiral structure. They'll look distorted, with long tails of stars stretching into space. These tidal tails can extend for hundreds of thousands of light years, creating some of the most beautiful structures in the universe. We see these tails in other colliding galaxies, and they're absolutely stunning. By the third or fourth pass, the galaxy's cores will merge. This is when things get really intense. The supermassive black holes will begin their final death spiral, orbiting each other at incredible speeds. Einstein's general relativity predicts that they'll lose energy by radiating gravitational waves, causing them to spiral closer and closer until they finally merge in a violent burst of gravitational radiation. But what about all the smaller galaxies in our local group? They're not just spectators, they're participants. The large and small Magellanic Clouds currently orbiting the Milky Way might be stripped away during the collision. They could end up orbiting Milkomeda at a much greater distance, or they might be torn apart entirely, their stars scattered across intergalactic space. The Triangulum Galaxy, currently about 3 million light-years away, faces an uncertain fate. Some simulations show it merging with Milkomeda shortly after the main collision. Others show it being ejected from the local group entirely, doomed to wander alone through the expanding universe. The exact outcome depends on details we can't yet measure precisely: the galaxy's exact velocities, their dark matter distributions, and the gravitational influence of more distant galaxies. Recent observations have revealed even more complexity. The Milky Way and Andromeda aren't approaching each other in a straight line. They have what astronomers call transverse motion, sideways movement that affects how they'll collide. It's like two cars approaching an intersection at an angle rather than head-on. This transverse motion, measured precisely by the Hubble and Gaia telescopes, shows that the collision might be more of a glancing blow than a direct hit. This is actually good news for star systems like ours. A glancing blow means less disruption, less chance of stars being ejected, and a gentler merger overall. It's the difference between a demolition derby and a carefully choreographed dance. Both are collisions, but one is much more elegant than the other. The collision will also affect the cosmic web, the large-scale structure of the universe. Right now, the local group is falling toward the Virgo cluster, a collection of over 1,000 galaxies about 50 million light-years away. After the merger, Milkomeda will continue this journey, but as a single, more massive galaxy. In the very far future, perhaps hundreds of billions of years from now, we might merge with the Virgo cluster itself. But long before that happens, the universe itself will have changed dramatically. Dark energy, the mysterious force causing the universe's expansion to accelerate, will have pushed most galaxies beyond our cosmic horizon. The universe will become a lonelier place with vast voids between galaxy clusters that can never be crossed. This cosmic isolation makes the Andromeda collision even more significant. It's not just a merger, it's the creation of our permanent cosmic home. Milkomeda will be our island universe, containing all the stars and planets that future civilizations in our corner of space will ever be able to explore. It's like Earth's continents coming together to form a supercontinent, but on a galactic scale. The collision will also create new types of stars that don't exist today. When gas clouds collide at high speed, they can form very massive stars, monsters with 50 or even 100 times the mass of our Sun. These titans live fast and die young, burning through their fuel in just a few million years. When they explode, they create some of the most energetic events in the universe, hypernovae and gamma-ray bursts. These gamma-ray bursts are so powerful they can be seen across the entire observable universe. For a few seconds, a single exploding star can outshine an entire galaxy. If one happened close to an inhabited planet, it could strip away the ozone layer and trigger a mass extinction. But don't worry, space is so vast that the odds of a gamma-ray burst hitting any particular planet are astronomically small. The collision will also create exotic stellar remnants. When massive stars explode, they leave behind neutron stars, city-sized objects with the mass of the Sun, where a teaspoon of material weighs as much as Mount Everest. Some of these neutron stars will collide with each other, creating kilonovae, explosions that forge gold, platinum, and other heavy elements. In 2017, astronomers detected gravitational waves from a neutron star collision and saw the kilonova that followed. It created more gold than the mass of Earth, scattered into space to eventually become part of new planets. Think about that. The gold in your jewelry, the platinum in your electronics, even the uranium that powers nuclear reactors, all came from these cosmic collisions. The merger of the Milky Way and Andromeda will create tons of these precious elements, seeding future generations of planets with the materials needed for technology and perhaps life. But let's talk about something even more mind-bending: time dilation. According to Einstein's relativity, time moves differently in strong gravitational fields. Near the merging supermassive black holes, time would slow to a crawl. If you could somehow observe the merger from a safe distance near the black holes, millions of years would pass in the outside universe, while only days passed for you. It's like nature's ultimate time machine. This time dilation effect has been confirmed by experiments on Earth and observations of stars orbiting our galaxy's central black hole. The star S2, which orbits Sagittarius A star every 16 years, experiences time dilation that we can actually measure. When the black holes of the Milky Way and Andromeda merge, the time dilation effects will be thousands of times stronger. Now here's something that showcases just how far our understanding has come. In 2020, astronomers announced the discovery of a massive gas halo around Andromeda, extending over 1 million light-years from the galaxy. This halo is already touching the outskirts of the Milky Way's own halo. In a sense, the collision has already begun. We're already exchanging gas with Andromeda, even though the galaxies themselves are still 2.5 million light-years apart. This discovery came from studying quasars, incredibly bright galaxies powered by feeding supermassive black holes. By observing how quasar light passes through Andromeda's halo, astronomers could map its extent and composition. It's like using distant lighthouses to map fog banks on Earth, but on a cosmic scale. The halos contain enough gas to make billions of new stars. As the galaxies approach, these halos will compress and mix, potentially triggering star formation long before the main disks collide. We might see a ring of new stars forming in the space between the galaxies, like a cosmic pearl necklace connecting them. But what really captures my imagination is how this collision connects to the search for extraterrestrial intelligence. The Drake equation, formulated by astronomer Frank Drake in 1961, tries to estimate how many communicating civilizations might exist in our galaxy. One crucial factor is the rate of star formation, which creates new homes for potential life. The collision with Andromeda will dramatically increase star formation, potentially creating billions of new habitable worlds. If even a tiny fraction of these worlds develop life, and a tiny fraction of that life becomes intelligent, Milkomeda could be teeming with civilizations. The collision might not just be creating a new galaxy, it might be creating a cosmic community. SETI, the Search for Extraterrestrial Intelligence, has been listening for signals from alien civilizations since the 1960s. So far, we've heard nothing but silence. But maybe we're just early to the party. Maybe the real explosion of intelligence in our galaxy will come after the collision, when all those new stars and planets provide fresh opportunities for life to emerge and evolve. The collision will also affect how civilizations could travel between stars. Right now, the stars in our galaxy are relatively well organized in a flat disk with spiral arms. After the merger, stars will be scattered in all directions, some much closer together, others much farther apart. Some regions of Milkomeda might be perfect for interstellar travel, with stars packed close enough that journeys between them take years instead of millennia. Imagine a future where civilizations hop from star to star, like island hopping across an ocean. The collision could create stellar archipelagos, chains of stars close enough for easy travel. These could become the highways of a galactic civilization, connecting worlds across Milkomeda. But there's also a darker possibility. The chaos of the collision could make interstellar travel more difficult. Stable planetary orbits might be disrupted, asteroid belts could be scattered, increasing the risk of impacts. The increased radiation from all those new stars and supernovae could make space travel more dangerous. The collision could isolate civilizations rather than connect them. Recent studies of exoplanets, planets orbiting other stars, have shown us just how diverse and resilient planetary systems can be. The Kepler Space Telescope discovered planets in binary star systems, planets orbiting dead stars, even rogue planets wandering between the stars. This diversity gives us hope that many worlds will survive the collision intact. The TESS mission, launched in 2018, is finding planets around nearby stars, giving us a census of worlds in our cosmic neighborhood. By the time Andromeda arrives, we'll have catalogued millions of planets, understanding which types are most likely to survive galactic collisions. This knowledge could be crucial for any civilization planning for the long-term future. But let's zoom back out to the biggest picture. The collision of the Milky Way and Andromeda is happening in the context of an accelerating universe. Dark energy is pushing galaxies apart faster and faster. In about 1 trillion years, the cosmic expansion will be so fast that light from distant galaxies will no longer be able to reach us. The observable universe will shrink to just our local group, or rather to Milkomeda and a few small companion galaxies. This means the collision is creating what will essentially become the entire observable universe for far future civilizations. Everything they will ever be able to see or explore will be contained within Milkomeda. It's both limiting and liberating, a smaller stage, but one where every star is within reach given enough time and technology. The collision also raises profound questions about information and memory. Right now, we can look out and see galaxies as they were billions of years ago. We can study the history of the universe by looking deeper into space. But after the collision, in the far future when other galaxies have vanished beyond the cosmic horizon, how will civilizations learn about the universe's past? They'll have to become cosmic archaeologists, studying the stars in Milkomeda to piece together its history. Every star carries clues about when and where it formed. By analyzing stellar populations, future astronomers could reconstruct the collision, identifying which stars came from the Milky Way and which from Andromeda. It would be like reconstructing Earth's continental drift by studying rocks and fossils. This archaeological approach is something we're already doing. The European Space Agency's Gaia mission has created a three-dimensional map of over 1 billion stars, measuring their positions, distances, and motions with unprecedented precision. This data has revealed stellar streams from ancient collisions, showing us that our galaxy's history is written in the motions of its stars. The collision will also create new types of astronomical objects we've never seen before. When two spiral galaxies merge, they can create shell galaxies, beautiful structures where stars orbit in nested shells like cosmic Russian dolls. NGC 474, about 100 million light-years away, is a perfect example. Its delicate shells tell the story of a merger that happened 1 billion years ago. Ring galaxies are another possibility. If the collision happens at just the right angle and speed, it could create a density wave that propagates outward like a ripple in a pond, triggering star formation in a perfect ring. The Cartwheel galaxy, 500 million light-years away, shows us how spectacular these structures can be. Imagine looking up at a ring of brilliant blue stars encircling the entire sky. But perhaps the most intriguing possibility is that the collision could create conditions we've never seen before. When you mix two unique galaxies with their own histories, compositions, and dynamics, you might get something genuinely new, perhaps unique types of star clusters, or regions where the physics of star formation works differently than anything we've observed. The collision will also be a test of our physical theories on the grandest scale. General relativity, quantum mechanics, dark matter, dark energy, all our fundamental theories will be put to the test. If our predictions about the collision turn out wrong, it could point to new physics, new forces, or particles we haven't discovered yet. Already, observations of other colliding galaxies have surprised us. Some mergers produce way more stars than our models predicted. Others produce fewer. Some create unexpected structures that challenge our understanding of gravity and gas dynamics. Each surprise is a clue that we're missing something important about how the universe works. The Nancy Grace Roman Space Telescope, set to launch in the mid-2020s, will survey millions of galaxies, including many in various stages of collision. By studying this cosmic collision census, we'll refine our models and better predict what will happen when our turn comes. It's like watching other dancers to learn the steps before our own performance begins. But here's what really gets me excited. The collision represents transformation on a scale we can barely imagine. Two galaxies, each with its own identity and history, will become something entirely new. It's death and rebirth on a cosmic scale, destruction that leads to creation, chaos that produces new forms of order. This pattern, transformation through collision, appears everywhere in nature. Atoms collide to trigger nuclear fusion in stars. Continents collide to build mountain ranges. Ideas collide to create innovations. Even at the quantum level, particles collide and transform into new particles. The universe seems to have a fundamental rule. Bring things together with enough energy and something new emerges. The collision of the Milky Way and Andromeda is this universal principle writ large across the cosmos. It's the same process that created the galaxies in the first place, just continuing on a grander scale. We're not witnessing a unique event, we're seeing the universe doing what it always does, building complexity through interaction and collision. And here's a beautiful thought. Every atom in your body has been through multiple stellar collisions already. The carbon in your DNA was made in a star that died billions of years ago, scattering its ashes into space. Those ashes became part of new stars, which also died and scattered their remains. Through cosmic recycling, those atoms eventually became part of the cloud that formed our Sun and Earth. You are made of ancient stardust that has traveled across the galaxy, participating in the cosmic dance of creation and destruction. The atoms reading these words have been on an incredible journey through space and time, and they're not done yet. In 4 billion years, those same atoms might be part of a new star, a new planet, or even new life in Milkomeda. This cosmic recycling extends to entire stellar systems. When galaxies collide, some planetary systems get disrupted, but others remain intact. Computer simulations show that most planets will stay bound to their parent stars, continuing their orbits as if nothing happened. Life, if it exists on these worlds, might not even notice the galactic collision happening around them. Think about that. Entire civilizations could rise and fall during the collision, never knowing they're living through one of the most dramatic events in galactic history. It's like bacteria living on a dancer, unaware of the dance. Scale matters in the universe, and what seems catastrophic from one perspective might be invisible from another. Recent discoveries have made this even more fascinating. The TRAPPIST-1 system, just 40 light-years away, has 7 Earth-sized planets orbiting a small red dwarf star. 3 of these planets are in the habitable zone where liquid water could exist. Red dwarf stars live for trillions of years, far longer than the collision will take. Systems like TRAPPIST-1 could remain stable throughout the merger, providing safe harbors for life. The James Webb Space Telescope is studying the atmospheres of these exoplanets, looking for biosignatures, signs of life. By the time Andromeda arrives, we might know of thousands of inhabited worlds. The collision won't be just a merger of stars and gas, but potentially a merger of biospheres, bringing together life from 2 galaxies. But what about artificial intelligence and machine civilizations? In 4 billion years, biological intelligence might be obsolete, replaced by AI that can survive in the harsh environment of space. These machine minds wouldn't need planets. They could exist in spacecraft, asteroid bases, or even in the computational substrate of advanced technology we can't imagine. For machine civilizations, the collision might be an opportunity rather than a threat. The chaos and energy of the merger could provide raw materials and power sources. They might surf the gravitational waves, using the changing space-time to propel themselves across the galaxy. What seems like destruction to us might be a cosmic buffet for them. The collision will also create extreme environments that could harbor exotic forms of matter. Near the merging black holes, the intense gravity could create quark stars, objects denser than neutron stars where quarks, the building blocks of protons and neutrons, are squeezed together. These hypothetical objects would be laboratories for physics beyond anything we can create on Earth. String theory, one of our attempts to unify quantum mechanics and general relativity, predicts extra dimensions beyond the 3 spatial dimensions we experience. The extreme conditions during the black hole merger might make these extra dimensions detectable. Future physicists studying the collision could finally answer whether we live in a 10-dimensional universe, as string theory suggests, or something else entirely. But let's bring this back to the human experience. Throughout history, the night sky has been our companion, our calendar, our navigation system, and our inspiration. Every human culture has stories about the stars. The collision with Andromeda will fundamentally change this sky that has been constant throughout human history. Imagine the cultural impact. Religions might interpret the approaching galaxy as divine intervention. Artists will create works inspired by the changing heavens. scientists will have front-row seats to cosmic physics. Children will grow up with two galaxies in their sky, thinking it normal, while their grandparents remember when there was only one. The collision could unite humanity, or whatever we've become, in a shared cosmic experience. Just as solar eclipses bring people together in wonder, the slow-motion collision could be a unifying force across millions of years. It might inspire a golden age of exploration as civilizations work to understand and perhaps even influence the merger. Could future technology actually influence the collision? It seems impossible now, but we're talking about billions of years of potential technological development. Perhaps future civilizations could use stellar engineering to adjust star orbits, creating safe zones within the chaos. They might build megastructures to harvest energy from the collision, turning destruction into power. The Kardashev scale, proposed by Soviet astronomer Nikolai Kardashev in 1964, classifies civilizations by their energy use. A Type 3 civilization could harness the energy of an entire galaxy. The collision might be an opportunity for a Type 2 civilization, using the energy of a single star, to become Type 3, learning to manipulate galactic-scale forces. But even without such advanced technology, the collision offers incredible opportunities for energy harvesting. The accretion disks around the merging black holes will shine with the light of trillions of suns. Advanced civilizations could build collectors around these disks, gathering more energy than they could ever use. It would be like building a dam on a cosmic river. The collision will also affect cosmic rays, high-energy particles that zip through space at nearly the speed of light. The shock waves from colliding gas clouds will accelerate particles to incredible energies, creating a galaxy-wide particle accelerator. These cosmic rays influence planet atmospheres and might even affect the evolution of life by causing mutations. Recent observations of cosmic rays from other galaxies have shown us just how powerful these galactic particle accelerators can be. The Pierre Auger Observatory in Argentina has detected cosmic rays with energies millions of times higher than anything we can create in our particle accelerators. When Milkomeda forms, it could become one of the most powerful cosmic ray sources in the local universe, affecting planets millions of light-years away. But perhaps the most profound aspect of the collision is what it teaches us about our place in the universe. We often think of ourselves as separate from the cosmos, looking up at the stars from our small planet. But the collision reminds us that we're participants in a grand cosmic dance that's been going on for nearly 14 billion years. Every galaxy we see has been shaped by collisions. Every heavy element in the universe was forged in stellar deaths triggered by galactic interactions. Every planet orbits a star that was born from gas clouds compressed by gravity and galactic dynamics. We're not just observers of the universe, we're products of it, made by the very processes we're studying. This perspective shift is what I call the cosmic perspective. It's the recognition that we're not separate from the universe, but deeply embedded in it. Our atoms, our energy, our very existence is woven into the fabric of space-time. When we study the collision of galaxies, we're studying our own history and future. Carl Sagan famously said, "We are made of star stuff." But it goes deeper than that. We're made of collision stuff, merger stuff, cosmic recycling stuff. We're temporary arrangements of atoms that have been on an incredible journey and will continue long after we're gone. The collision with Andromeda is just one chapter in their story. And what a story it is! From the Big Bang to the formation of the first stars, from the assembly of galaxies to the emergence of life, from the evolution of intelligence to whatever comes next, it's all one continuous narrative. The collision with Andromeda isn't an ending, but a transformation, a plot twist in a story that will continue for trillions of years. This cosmic story gives me hope. Yes, our sun will die. Yes, Earth will become uninhabitable. Yes, even Milkomeda will eventually fade as the universe expands and cools. But along the way, there will be countless opportunities for new worlds, new life, new intelligences to emerge and add their own chapters to the story. The collision also reminds us of the importance of perspective and time. What seems like a catastrophe on one timescale might be creation on another. What appears chaotic up close might reveal beautiful order from afar. The universe operates on scales so vast that our human intuitions often fail us. We need science, mathematics, and imagination to truly grasp what's happening. And here's something that fills me with wonder. We've figured this out. Humans who have existed for just a cosmic eye blink have developed the tools and theories to predict events billions of years in the future. We've built telescopes that can see across billions of light years. We've created computers that can simulate the gravitational interactions of billions of stars. We've developed physics that describes everything from subatomic particles to galactic clusters. Think about what that means. The universe has evolved creatures capable of understanding the universe. It's as if the cosmos has developed eyes to see itself, minds to comprehend itself. Through us, and perhaps through countless other intelligences across the cosmos, the universe is becoming self-aware. The collision with Andromeda is part of this cosmic self-awareness. By studying it, predicting it, and preparing for it, even if only intellectually, we're participating in the universe's journey toward greater complexity and consciousness. We're not passive victims of cosmic forces, we're active participants in the cosmic story. As I think about all of this, I'm filled with a profound sense of gratitude. How lucky we are to live in a time when we can understand these cosmic processes. How fortunate that we exist at all, given the incredible chain of events that had to occur for Earth to form, life to emerge, and intelligence to evolve. We're witnessing the universe from a privileged vantage point, able to look back at its history and forward to its future. So when you look up at the night sky and see that faint smudge of light that is Andromeda, remember, you're looking at our future dance partner. Those photons hitting your eyes have traveled for 2.5 million years to bring you news of a galaxy we'll one day merge with. You're connected to it across space and time, part of the same cosmic web of matter and energy. The collision of the Milky Way and Andromeda isn't something to fear, it's something to marvel at. It's the universe in action, creating and transforming on the grandest possible scale. It's a reminder that we live in a dynamic, evolving cosmos where even galaxies dance, merge, and create new realities. And perhaps most importantly, it's a call to appreciate the incredible cosmic moment we're living in right now. We have the knowledge to understand our place in the universe. We have the technology to explore it. We have the imagination to envision its future. We are the universe contemplating itself, and that might be the most beautiful thing of all. So the next time you're outside on a clear, dark night, take a moment to look up. Find Andromeda if you can. It's in the constellation of the same name, visible in autumn and winter from the northern hemisphere. As you gaze at that distant galaxy, remember that you're looking at billions of stars that will one day merge with our own. You're glimpsing our cosmic future, written in light that's older than our species. And in that moment, feeling both infinitely small and part of something infinitely vast, you'll understand what it truly means to be a child of the cosmos, made of ancient stardust, witnessing the universe's grand story unfold. That's the gift of the cosmic perspective. And it's yours for the taking every time you look up at the stars. If you enjoyed this video, make sure to check out this other one at the left side of the screen. What is the largest thing in the universe? Discover what is the largest thing in the universe by learning how astronomers use the Hubble Space Telescope, James Webb Space Telescope, and Sloan Digital Sky Survey to map billions of galaxies and reveal structures like the Sloan Great Wall, Hercules Corona Borealis Great Wall, Laniakea Supercluster, and much more. See you there.